Chemistry is a science that's based on electrons. In chemistry, substances or reactants react with each other or with reagents under certain chemical conditions to produce new substances or products. In order to understand chemical reactions, we need to understand bonding, we need to understand molecular structures. Let's take, for example, the simplest alkane possible, which is methane. Methane has a chemical formula of CH4. In order to draw a Lewis structure for methane, we need first to calculate the total number of valence electrons in this compound. For carbon, for example, the number of valence electrons is 4 because carbon is located in group 6A. And of course, there's 1 valence electrons in each of these hydrogen atoms. So the total number of valence electrons in this case is 8. So what we can do is we draw the central atom, which is carbon, and then we draw the surrounding atoms, which are hydrogens, and there are 4 of them, and then we draw a bond between carbon and each of these hydrogen atoms. Now, in order to understand or to get a true picture of bonding in this compound, we need to recall the electronic configuration of carbon. Again, remember, carbon is in group 6A. The total number of valence electrons, or the number of valence electrons in this case, is 4. Okay, so this is the electronic configuration of carbon. It's 1s, 2, 2s, 2, 2p, 2. In order to understand bonding, we need to distribute these electrons, or the valence electrons, the electrons in the outermost shell, or the highest principal quantum level. In the case of carbon, we need to be able to distribute them in these orbitals. So we are talking basically about the 2s and the 2p orbitals. Obviously, there are 3 2p orbitals. Okay, so there are 3 of them. This is 2p x, this is 2p y, and that's 2p z, and this is the 2s orbital. Now, the valence electrons are these ones, okay, which are located in the outer most shell, okay, shell number 2. Obviously, these two electrons in the 1s orbital are called core. Okay, it is the valence electrons that are responsible in bonding always in compounds. Okay, so in order to understand bonding again, we need to distribute electrons in these orbitals. So there are 1 2s and 3 2p orbitals, and each of them contain an unpaired electrons according to this arrangement, which is based on the basic chemical rules or principles such as the Pauli exclusion principle and Hund's rule. According to this electronic arrangement, carbon can make 4 bonds, which is reasonable because carbon does make 4 bonds as usual. Okay, but this may not be the true picture in the case of methane and in the case of all carbon-containing compounds, because we know carbon, in the case of methane, has a tetrahedral shape. All bonds in methane, all CH bonds are actually equivalent, not only in bond strength, but also in bond length. They are all equivalent. The angle is 109.5 in this compound, okay, or in sp3 hybridized carbons. And we say sp3 hybridized carbons, which means that these orbitals will have to mix. And if they do, we get 4 brand new orbitals as a result of mixing of the 2s and the 3 2p orbitals. So we get 4 hybrid orbitals, and of course there is 1 unpaired electron in each of them, and the hybridization type in this case is sp3, and it is called sp3 because 1s and 3p orbitals are mixed in this process. These hybrid orbitals are in between, if you like, in characteristics, or of intermediacy in characteristics between those of p and s orbitals. In order to understand the concept of hybridization, let's do a little experiment. Okay, we have here, this is orange juice and this is berry juice. So what we'll do is we'll mix these two together. Now, since 1s in this case was mixed with 3p orbitals, so therefore the ratio in terms of volume should be 1 to 3. So let's take, for example, 50 ml of a berry juice in this conical flask. So something like that. So that's roughly 50 ml of a berry juice. And now what we need to do is we need to add 3 times this amount in volume of orange juice until basically we reach 200 ml. So that's what we get, and then we shake, and if you look carefully at the color of this brand new juice, which was obtained as a result of mixing berry juice with orange, you can see that the color is somewhat in between, okay, the colors of orange and berry, and probably not only the color but also the taste as well. So this is a little experiment, a very simple experiment, which illustrates the concept of hybridization. The color is somewhere in between, if you notice, okay, and then probably also the taste is somewhere in between. So we can think of this like an s orbital. These are p orbitals, okay, and these are the sp3 hybrid orbitals. So there are 4 of them in this case. In the case of methane, 4 sp3 hybrid orbitals. We can draw the central carbon atom like that again, and now we can draw these orbitals. And if you recall, the shape of a p orbital is actually like that. So it's like a dumbbell shape, and the s, of course, is spherical. And the shape of sp3 hybrid orbitals should be somewhere in between. So something like that. Okay, again, recall the intermediate color of that brand new juice, or hybrid juice, if you like. We can call it also hybrid because it's obtained as a result of mixing these 2 juices, orange and berry. Okay, if we draw the central carbon atom like that, okay, of course there are 3 sp3 hybrid orbitals around it. Okay, so that's 1, that's 2, 3, and 4. And of course we need to draw the hydrogen atoms. So this is hydrogen here, hydrogen here, hydrogen, and hydrogen here. And the type of orbital that's used in bonding, okay, from hydrogen in this case, is of course a 1s orbital, which is spherical in shape. So we should do that in all of these bonds. And you can see clearly the point of overlap between the 1s orbital from the hydrogen atom and the sp3 hybrid orbital from carbon. So this is sp3, 1s from hydrogen, sp3 from carbon, 1s from hydrogen, sp3 from carbon, and 1s from hydrogen. We can see the point of overlap when these orbitals overlap with each other, head to head, if you like, or end to end. Okay, this constitutes what's called a sigma bond. Okay, so there are 4 sigma bonds in the case of methane, which are formed by head to head overlap or end to end overlap between sp3 hybrid orbital from carbon and an s orbital from hydrogen. The angles again in the case of methane are 109.5, and this is called the tetrahedral angle. The molecular or the electron arrangement of electron pairs around the central carbon atom in the case of methane is tetrahedral. The molecular shape is also tetrahedral here as well. Okay, that's because there are no lone pairs. All electron pairs are bonding.